Okay, so yeah. Mm, okay. So welcome. Good morning. Welcome to the seventh lecture of Web of Data. Today we're going to move on to a new topic. You might already have seen enough of OWL. So we're going to move on to a new section of the course. So what is this section? We're going to start talking about Sparkle. So the last time we spoke about RDFS and OWL, we spoke about logic and ontologies and how to use these languages in order to describe data with well-defined meaning. So we mainly were focused on the logic part here. This is based on rules, but we were using ontologies. We had previously seen data. And the next part up is queries. Yeah, so we're going to talk about querying the semantic web or the web of data using Sparkle. So the language that we use for querying RDF, the standard language, is called Sparkle. So there's two versions, Sparkle 1.0 and then a later extension 1.1. And we're going to talk about 1.0 today. So we're going to talk about the original version. And then in the next class, we'll talk more about Sparkle 1.1. So we have this lovely RDF graph. Sorry if I start scratching myself. I'm allergic to mosquitoes and I got bitten all over last night. Very annoying. So we have this lovely RDF graph that describes Sharknado, Sharknado 2, Sharknado series. We have some actors and so forth. And what we'd like to do with this RDF graph is to ask some questions. So to answer some questions over this RDF graph, yeah? So we're going to use the Sparkle query language for this. What we'd like to ask over this graph is who stars in Sharknado, yeah? So if we look at our graph, we see, okay, we have Sharknado here. Actually, I forgot to upload the slides as well. If somebody wants the slides to be uploaded, it will take me a minute. Will I take a minute to upload the slides? Or like upload the slides? Yeah, okay. So, has anyone actually ever seen Sharknado? No? No? I've never seen it either. So the history behind Sharknado was in the very first time I gave this course, I wanted to show that there's RDF on the web. So I went to IMDb and I asked for a suggestion for a movie, and immediately a student called out Sharknado. So then I just based all of the examples on Sharknado. So that's the history. I hadn't prepared everything. So give me 1 second. Teaching web of data and it. Teaching. 1 second. Classes 23. Lectures. And it. Over here. And edit this. And put this here. And delete this for now. Okay, so sorry about that. So the class should be on the homepage now. Okay, so we have an RDF graph. Oh, what happened? We skipped a slide. Come back here. Who stars in Sharknado? So if we look at our RDF graph, we see that we have two good answers. We have John Hurd and we have Ian Ziering here. Yeah. So the question then is, how do we formulate this as an actual query in a query language? We're going to use a query language called Sparkle. So here's our query in Sparkle. We'll explain some details of it later, but the main thing here is we have some turtle-like syntax in this where clause, which says Sharknado stars, and then it has a variable marked with the question mark, star. And we're going to try to match this where clause into the graph. So we're going to talk a little bit more about this later, but intuitively what we're going to get here as solutions would be John Hurd and Ian Ziering, because these match this variable here. Yeah. Okay, so come Okay, so let's go through that one by the queries, language part piece by piece. The first thing we have, not very interesting, but very useful, is prefix declarations. So rather than give full IRIs every time, we can declare some prefixes at the start. So we have some shortcuts for IRIs, exactly as in Turtle. In this case, our prefix, we say example, EX, and then we give some value, and then we can use this prefix here. And we've seen all this before in Turtle many times. It's the exact same idea. Yeah. So the interesting part is the where clause. So the where clause is where all the magic happens. Yeah. So this is where we specify what to match in the data. So this is the most interesting part of our query. So this is where we can do joins, we can do selections, we can do unions, we can do property paths, we can do a bunch of stuff that we're going to see, yeah, in this class and the next class. So where is what we specify what we want to match in the data? In this case, what we have is essentially a triple, Sharknado, stars, and a variable called star. Yeah, so it's basically we're going to be basing our where clause on triple patterns. What is a triple pattern? It's a triple with variables. Yeah, so we now have this question mark thing, which is a variable, and we can put variables in any place we'd like to. So when we apply this, what we're saying basically is that we are looking for triples where the subject is Sharknado, the predicate is stars, and the object can be anything. And we'd like the object to be returned, please. Yeah. So when we run this query on this data, we say, okay, this triplet here has Sharknado, the predicate is stars, and we want to return John Hurd. Yeah. Sharknado, the predicate is stars, and we want to return Inzeri. So here's one match here, and here's another match here. Yeah. So we get two results. Yeah, John Hurd and Inzeri. We can have a slightly more complex example to illustrate other types of features in the where. This time we're going to ask what movies did the stars of Sharknado also star in? So how do we formulate this question? Well, if we look at the graph, we know that John Hurd and Inzeri starred in Sharknado, and now we want to know what other movies they starred in. So at least in the case of Inzeri, we see that Inzeri also starred in Sharknado too. Yeah. So what we need here intuitively in a relational database setting is a join. Yeah. In Sparkle, we have an even more intuitive way of writing these sorts of joins called natural joins or equi-joins, where we just write the graph pattern. So we just write out the graph, and then we say we leave the things we're looking for as variables. Yeah. So what does it mean? We have Sharknado star star, and we have movie star star. So we have two variables here, movie and star. So in the first triple, we're looking for Sharknado star star, just as before. And then for these stars, we're looking at what other movies they might have starred in. Yeah. So how many solutions do you think we would get for this query on this graph? So we have Sharknado. Yeah, we're looking for a subject. Stars star. This would be Inzeri. We can map Inzeri to star here. And then we're looking for movie star star. So we have Inzeri, and we can go backwards stars, and we can get Sharknado 2 as a result, right? So we get one result, or do we get more results? 2? What would the second result be? Sharknado, right? So we could go from Sharknado stars Inzeri, and why can't we go back simply and go star Sharknado? Yeah, we haven't limited that result. There is another result. What's the other result? Sharknado again. Sharknado, John Hurd. Yeah. So Sharknado, John Hurd, Sharknado. Yeah, so we actually get 3 results here. So here's one result. As we saw, this is the intuitive results. We get another result here, which is John Hurd, Sharknado. So we go back to Sharknado, which is fine. And here we have another result here, which is Sharknado stars Inzeri, and we go back to stars and we get Sharknado again. Yeah, so this is called a graph homomorphism, effectively. What we're computing here is a homomorphism from this where clause to the data graph. Yeah, and we get these 3 results here, these 3 solutions. Inzeri, Sharknado 2, Inzeri, Sharknado, John Hurd, Sharknado. So this is the basis of Sparkle. This is the key concept, this idea of basic graph patterns. We can have 2 triple patterns, we can have 3 triple patterns, we can have 4 triple patterns, and intuitively in a relational database setting, what we're doing is computing joins between the common variables of these triple patterns. Yeah, it's completely equivalent to joins, or if we look at it from a graph perspective, it's equivalent to graph homomorphisms. Okay. So this is called the basic graph pattern. This is essentially just a set of triple patterns. The order doesn't matter. We have to write the triple patterns in some order, but The order doesn't really matter. That's why we call it a set of triple patterns. The order we evaluate it in can have an effect on performance, but in terms of what results we get, it doesn't really matter, much like joins in relational databases. And we can draw it as a graph. So we can see it exactly as a graph in the sense we can draw, because we have triples, every triple refers to a directed labeled edge. We can draw our basic graph pattern as a graph, and then we can somehow say that there's a homomorphism from this graph pattern here to this graph where we keep the constants, the identity of constants. Yeah. Okay, here we call these a join variable. So we say that there's a join variable here, and basically we're going to have a natural join between the triple patterns based on the common variables appearing. Any questions or doubts about that? Nope. Okay, so another super common thing that we have in the relational algebra, and we have in SQL and so forth, is the idea of disjunction, or what we would call union. Yeah, or. Yeah. So in this case, what we're looking for are the titles of the first two movies in the Sharknado series. So we're looking for the titles of the first two movies. We have Sharknado, title of Sharknado, and Sharknado 2, title of Sharknado 2, the second one. Very creative title. And we'd like to ask this. So we're going to do this by naming both of the movies. Yeah. So what we're going to ask for is the title of Sharknado or the title of Sharknado 2. And we can do that with this query here, where essentially we now compute a union of triple patterns. Yeah. So here we have one triple pattern, and then we take the union, and then we have another triple pattern, and then we can do a join with the title. Yeah. So here we're getting, for movie, we're getting movie should be bound to either, oh no, sorry, we're not naming these directly. We're using the first movie or second movie property. So we're getting the first movie of the Sharknado series, union, the second movie of the Sharknado series. And then we do a join to get the titles of those movies. Yeah. So what will this get us? This will get us the following solutions here. Sharknado, title, Sharknado 2, the second one, title, and so forth. Yeah. Okay. Give me the titles of all movies, and if available, their first aired date. Yeah. So this is a little bit different. Do you know what relational algebra operator this would correspond to? If available, does that ring any bells? It's a particular type of join called an outer join. Yeah. So we're looking for an outer join, which means keep, let's say if it's a left outer join, keep the table on the left and try to extend it if possible with the right, but if not, you still keep the results. Yeah. So we're going to get the titles of all movies, and if available, the first air date. So to get the titles of all movies, we want to get the things that are of type movie. So we're going to do like a variable movie, type movie, and then variable movie, title. Yeah, that will get us the titles of all movies. And then we can use a left join, what's called in Sparkle an optional pattern. Yeah. So in our query, what we have here is we have movie, a movie, title. We have optional, an optional pattern that says movie, first aired date. And we have a variable here to capture the date. So the point in this case is that Sharknado is a movie, so we get its title. Sharknado 2 is a movie, so we get its title. We have a first air date for Sharknado, which we can return, but we don't have a first air date for Sharknado 2. So we return Sharknado 2, still the title, but we return what's called an unbound, or it would be a null in relational databases. Yeah. So very similar to a left join. In this case, in the SQL or relational algebra. So this is called an unbound variable, a variable without a binding in a solution. Filtering results. So what movies were first aired in 2004? Yeah. If we want to apply some sort of filter like this, what we can use is a filter operator, which is kind of similar to certain conditions we put in a where clause in SQL. Okay, so what we have here is movie, a movie, first air date, and then we have a filter. So we say the date must be greater than the 31st of December 2013 and must be less than or equal to the 31st of December 2014. Yeah. So this allows us to filter and to find all of the movies that were first aired in 2014, which in this case would be empty. We have no such results. We have no such data. So this is the filter clause. Yep. So empty results. So what happens if we try to apply some sort of filter where it doesn't actually really make sense? Yeah, what happens if we try to subtract a number from a string, or we try to compare a number to a date? What kind of result do we get? So in this case, Sparkle defines that there are certain operators that expect certain types. And if these types are not given, then a type error is returned. Yeah, so it says, I can't compare a string with a date. I can't subtract a string from a string, whatever it might be. So Boolean filter operators, the filters evaluate either as true, false, or error. And this is very important for RDF, not so much in relational databases, because we have a nice relational schema and we say that this column is varchar, or this column is int, or this column is whatever. In RDF, things can be much more diverse, yeah? So we can end up applying filters on types that we don't know what they are. So we're only going to return results in the case of true. Yeah, so we can get true, false, or error. We're only going to return values or results that evaluate as true. And then we need to think about, okay, if we have true, false, or error, we need a sort of a three-valued Boolean logic. Yeah. Okay. So what does it mean? Let's have a look and see if we can figure this out. So we have what's our classical truth table. Yeah. We have A or B, and A and B. Yeah, so you might recognize this syntax maybe from some programming languages. Yeah. So we have A or B, A and B. We have true, 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 false, true, false, false, true, true, false, 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 false. Yeah, classic. Yeah, nothing surprising there. What do we think would happen in the case of true and error? What do we think A or B should be? True, okay. What do we think A and B should be in the case of true error? No. So we think this should be true. What would true and error be? So I'll give you a hint. I'll tell you what the semantics is. If it doesn't matter what the value of error is, whether it's true or false, then we can get a true or false answer. If we need to know what the value of error would be, whether it's true or false, then we rather get error. Yeah. So in this case, we would get error, right? Because if this were true, then this would be true. If this were false, then this would be false. So it matters what the error would be. Yeah. So in this case, we're going to get error. Yeah. So true and error is error. So we have error and true. So A or B would be true again. This is just a symmetric thing, and this would be error. False and error. What do we think about A or B? False or error? Does it matter what the error would be? If the error were true, it would give us true. If the error were false, it would give us false. So what do we get? Error. Yeah. Okay. And then we have false and error. False. Doesn't matter if it's true or false, it will be false. Yeah. Okay, then we have error, false. So this is error or false will be error. Error and false will be false. And then we have error or error, which will be error, and error will be error. Yeah. So let's see how we did. So true, error, error, false, error. So this is how filters are applied with error. So we can also apply not. So basically not is quite simple. We have not, error is error. Yeah. So this is how things will evaluate. And then at the end, once we've applied all of our combinations of filters and so forth, all of our Boolean combinations, if the final result of the filter, if and only if the final result of the filter is true, will we return the results? Any questions or doubts about that? No. Okay. So this is a big difference with false, by the way, is the negation. Yeah, because not false is true. Yeah, but not error is error. So if we get an error, it will still be filtered, even if we not the error. Yeah. So some operators, mainly for reference in the slides. Let me go through them briefly. We have not, we have or and, we have equals, not equals. We have some inequalities, less than, equal to, not equal to. We can sum or subtract, or no, sorry, we can do positive or negative numbers. We can add, we can subtract, we can multiply, we can divide. And here you see that there are certain types. So these Boolean operators apply on Booleans. These can apply in any RDF term. These apply on any comparable, any sort of element that has a comparison that we can compare. This applies for numbers, and this also applies for numbers here. Yeah. So we have some explanation here of the types. Yeah. We also have functions for existence, equality. Just to mention that I'm kind of cheating slightly because some of these are in Sparkle 1.1. This is not all pure Sparkle 1.0, but it's just easier to present everything now. We have existence, equality, if, so we can check if the value is bound. We have a conditional, if some condition, then return this value, otherwise return this other value. This is a ternary operator. Coalesce, which will return the first term that's not unbound. Exists or not exists. Does some result exist for the subquery? Same term, are these two terms the same? Is this term in this list of other terms? Is this term not in this other list of terms? We have some functions on RDF terms. We can check if a term is an IRI, if it's a blank note, if it's a literal, if it's a numeric value. We can convert something to a string. We have language, data type, IRI, blank note, string, data type, string, line, UUID, and so forth. There's a bunch of things. Yeah. There. So I won't go through them all in detail because there's quite a few. We have strings. We can get the length of a string. We can get a substring. We can get uppercase converted to uppercase, lowercase, see if it starts with a certain value and so forth. Yeah. And we have a regular expression match here, which will allow us to check if a certain string matches a certain regular expression pattern. We have numerics, so we can, we already saw some operators like plus and minus, but we can also have some functions, like we can take the absolute value of n, we can do some rounding, we can take the ceiling or the floor, or we can take a random number in some bound. We have functions for time. We can do now to get the current date time. We can get the year from a date, the month or the day from the date. We can get the hours from a date, the minutes, the seconds, the time zone. Or the time zone as a string from a date. Yeah, so we can extract the different values of a date, do some processing. We have hashing functions, so we can take a string and apply some hashing, MD5 hash, SHA-1, SHA-256, SHA-384, SHA-512. I'm not sure if you've seen these SHA things before. These are hashes, some of them are cryptographic hashes, and the number indicates how many bits are in the resulting hash. Yeah, so the bigger the number, the more strong cryptographically strong is the hash. MD5 is not a very strong hash, nor is SHA-1. Yeah, there have been some attacks on these. Okay. So we can also cast between types. So we have here some sort of matrix which explains what kinds of types we can cast, and it's sort of more or less intuitive. It's as you would expect. So, for example, we can always cast from a float to a double. Yeah, we can always cast from a double to a float. Okay, we might lose some precision, but we can do that. We can cast from, let's say, Boolean. Actually, I don't know how that works, to a string. Okay, that one would be just true. We can also cast to an int. I'm not sure what that gives. Maybe it gives 1 if it's true and 0 if not. Not sure. We can also, in some cases, we have this m value. So we have the n value as well. For example, we cannot convert from a float to a date time. Yeah, that doesn't make sense. Yeah, so we have some no's, and then we have some m's which are maybes, which depend on the value. So for example, if our string contains the character 2, if it's just the character 2, we can convert that to an int. Yeah, because it's lexically valid. However, we couldn't convert p to an int because it's not a lexically valid integer. Okay. So that's again for reference to give some idea. We can do some casting between types. And okay, any questions about that? So we can do quite some manipulation with this language and lots of filters and so forth. So we now have a more complex word class. Apologies if it's a little bit difficult to see this. Actually, I'm just looking at the configuration of the room. It's not the best. It's like a small projector in a very long room. But in any case, okay. I could have made the text bigger maybe, but so we have here our query. We have Sharknado series, first movie, Union Sharknado series, second movie, optional movie, first air date. Then we have movie title, and then we're applying a filter with a regular expression saying that the title must satisfy this expression here, which is asterisk 0 to 9 asterisk. So does anyone know what this regular expression would do? So what's the intuitive explanation of this regular expression? It's basically asking for any title that has a number in it. Yeah, we want a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We want one of these characters in the title. So what solutions would this query return? So we're asking for the first movie or the second movie of Sharknado. If available, we're asking for its first air date. We're asking for its title, and then we're filtering the movies that don't have a number in their title. Yeah. So how many results do we think we get here? Okay, so let's go through it. We have Sharknado series first movie. Movie would be bound in this case too. Sharknado, right? And then we have Union Sharknado series second movie. So movie in this case would be bound to Sharknado 2. Yeah. So we have a table with movie, and we have Sharknado in one row, and we have Sharknado 2 in another row. Optional. And then we say movie first air date. So for Sharknado, we're going to extend that solution and get the first air date. In the case of Sharknado 2, we're going to extend it but with a blank. Yeah, so we're going to keep that result, but keep the first air date blank. Then we're going to find out the titles of the movie. So in the case of Sharknado, we have Sharknado, the first air date, 2013, and now we have the title of Sharknado. And then in the second row, we have Sharknado 2, blank for the date, and then we add the title of Sharknado 2, the second one. And then finally, we have this filter that says only keep the titles with a number. Yeah, so the Sharknado title, we look at it, no number, we remove that result, and we keep the Sharknado 2 results. Yeah. So the final solution will be this, where we have the movie, we have the title, Sharknado 2, the second one, and we have a blank first air date because we don't have a date for Sharknado 2. Yeah. So we get one result. Yeah. So why do we add a string here to title? In this case, since title has this language tag, what string does for us is it extracts the string form of the term. So it will just extract the string here without the language tag. I'm not actually sure if it's 100% necessary. I think it might also work without the string, but str means given an IRI, for example, convert it to a string so we can use string functions on it. Yeah.
Que no me queda claro cuál es la parte, todo lo que está abajo del opcional.
Yeah.
¿Es opcional?
No. So the optional here, it's just the next clause, which ends at this curly brace here. So optional takes on the right-hand side something with curly braces, and that defines the limit. Yeah. So it's the same with the union here, that we have some curly braces before and we have some curly braces after, and the union ends here. Yeah. Okay. So here we have an interesting example. We've seen pretty much all of the features of the where clause in Sparkle. And one might say, well, we're missing a bunch of stuff. From the relational algebra, for example, one thing we're missing is difference or minus or not exists. Yeah. However, we can model negation using this trick here. So we're looking for movies. We're looking for their first air date, and then we're filtering to say that the date should not be bound. Yeah. So what happens in this query? We first get the movies. So we get Sharknado and Sharknado 2 here. These are our two movies. We then say optional first air date. Okay, so we say Sharknado, we get the date 2013, 7/11. Sharknado 2, we have no date, so it's unbound. And then we say filter not bound date. So this only leaves the result for Sharknado 2. Yeah. So what are we doing here really? We're asking for the movies where there does not exist a date. Yeah, we're asking for the movies without a first air date. So this is what we get here. Yeah, so we have a blank here to say that Sharknado 2 has no first air date. So we can do negation with this weird kind of trick. You might have seen it in other languages, I'm not sure, but you can do like a left join and then a not bound or is null in SQL to model this sort of negation. Okay, so that's pretty much the where clause. Any questions or doubts? There's one thing I should probably go back here and highlight something. So our basic graph pattern here, what our basic graph pattern is doing, let's have a look at results here, sorry. What our basic graph pattern here is doing, this set of triple patterns, what it does is it extracts a table from our graph. Yeah, so we have a graph, we have a basic graph pattern over that graph, it generates a table like this. Yeah. So what can we do with these tables? We can apply the relational algebra. Yeah, like we saw in SQL. So that's what we're doing here. Yeah, we're using these basic graph patterns, which will extract a table from our graph. And then we have these SQL like operators like union or left join optional, yeah, filter and so forth that are essentially combining these tables into new tables or filtering these tables, applying selections and so forth. So basically what bridges between the graph world and the relational world are these basic graph patterns. Yeah, so we use basic graph patterns as our sort of base operator to extract a table from the graph, and then we use these typical relational operators to create more complex queries. Okay. It's useful to have that intuition. Questions, doubts? Okay, so we've seen where clause in Sparkle 1.0. There's a lot more in 1.1 that we'll have to discuss the next time. We've only seen one query type. There's 4. Yeah, but the where clauses are all the same. So before you're worried, like we'll have to discuss all of that again 4 times, no. The where clause remains the same. But we have 4 different types of queries. The first and most often used and most intuitive is the select. So we have select. Why is it the most intuitive? It's not inherently more intuitive. It's just you're used to it from SQL. So the first type of select query we have is select with asterisk, yeah, which says just return all of the variables. Give me all of the information for all of the variables. Project everything, yeah. So hopefully you took the relational database course and you saw select star in SQL, so this won't be so strange. So here we get our results, movie, a movie, and movie star star. So we're looking for all of the movies and their stars. So we get our results here. We get 3 results, and here's our table. Yeah, we return movie and we return star in the table. If we want to do projection, much like in SQL, we just add our list of variables that we want to return. Yeah, so we can just say select star. Yeah. In this case, we'll return only the values for star. So how many results will we get in this case? We'll get all of the stars, so we'll get John Hurd and Ian Ziering. However, we'll get 3 results. Why do we get 3 results? Yeah, we're going to get Ian Ziering twice, right? So if we look at our solutions, if we look at our original table, what we're doing is we're just ignoring this column, but we keep the multiplicity of the other columns. Yeah. So this is called bag semantics. Yeah. So we keep the multiplicity of the number of solutions that give rise to each value. Yeah. So we know that there's 2 solutions with Ian Ziering, so we return Ian Ziering twice. So this is called bag semantics. This is the number of results returned. This means that the number of results returned must correspond to the number of matches in the data, yeah, the number of base solutions that generate them. So, yep. If we want to remove that, we just add distinct, like in SQL. Select distinct star, and now we don't have any more duplicate results. Yeah, we deduplicate the solutions we return. Okay. So this is called set semantics. Yeah, so it means that each result row must be unique. So you probably would have seen this in SQL, relational algebra, set semantics, SQL is bag semantics, at least the classical relational algebra set semantics. Yeah. Okay, we also have this weird operator that does not exist in SQL, that the Sparkle people felt when they defined the language would be very useful, but almost there, nobody uses it. It's called reduced. Anybody want to guess what reduced does? Reduces the number of results. No, it's like a distinct, but a kind of an optional distinct. It says to the query engine, I don't care if there's duplicates or not. So do whatever is easiest for you. Yeah. So it says if it's easier for you to get rid of the duplicates, get rid of them. If it's not easier to get rid of the duplicates, then don't. Yeah. So the valid solutions here, we have some non-determinism now, which is a little bit messy, but valid solutions would be either return John Hurd in Zering or return John Hurd in Zering twice. Yeah. So why might it be beneficial to remove duplicates for the query engine? Because if it has to do a join, it probably doesn't want to do duplicate lookups. Yeah. But deduplicating has a cost because we need to remember what the solutions are, add them to a hash set or some sort of structure to make sure that we don't repeat them several times. So in some cases, it might be better to remove duplicates. In other cases, maybe not. So this reduce basically says to the query engine, do whatever you want, but nobody ever uses it. So yeah. So reduce says may, but do not need to return duplicates. This allows the engine to do whatever it thinks is the most efficient. But it's a nice idea, but nobody cares about the query engine, so nobody uses it in practice. Yeah. That's the first type of query. So the second type of query we have in Sparkle, and also this applies for Sparkle 1.1. There are 4 query types in Sparkle 1.1 as well. And the second query type we have is ask. Yeah. So ask is pretty intuitive. Ask just says basically return me a Boolean that indicates whether or not there is some match for this word clause. Yeah, whether or not this word clause would generate some solution. So it's equivalent to running select, see if there's any result, and if there is, then return true. So in the ask case, in this case here, we say true because yes, there is a match for this word clause here. So that's all ask does. Returns true if there's a match, false otherwise. The match as well, I mean, okay, this is maybe getting a little bit detailed or into the weeds, but if there is a solution that's just unbound or everything is unbound, that's a match. So it will return true in that case as well. Yeah. So if there's any solution, even if the solution is blank, it will return true. Construct. Construct is an interesting case because in relational algebra, or relational databases, we apply queries over tables, we generate tables, and that's our result. So here we have graphs, and we're generating a solutions tables, which is a bit strange. So one might ask, why don't we have queries that generate graphs from graphs? Yeah. So this is what construct gives us. Construct allows us, it still passes through a table, so we're still somehow generating tables, and then from those tables generating graphs. But these queries allow us to generate a graph from a graph. Yeah. So we have the exact same format as before. We have our prefix declarations, we have our word clause, but now instead of a select, we have a construct and we have a basic graph pattern here again. So what this tells us is basically for all of the solutions for the word clause, we want to fill in the bindings, the results we got for each variable to create a new graph, yeah, according to this pattern. So in this case, we have where, movie a movie, movie star a star, yeah. And what we'd like to do now is we'd like to generate for all of the solutions here, we're going to generate a graph based on the set of solutions. So movie a movie, movie star a star. So here we have the movie, yeah. Sharknado, Sharknado 2. Then we have Sharknado stars John Hurd in Zering, and Sharknado 2 stars in Zering. And we're saying for each star, we want to say that their job is actor and generate a new graph based on this. So what will we get? We'll get a set of solutions like this, which will be actually RDF triples. So we'll get a new RDF graph based on the results of our query. Yeah. So construct allows us to generate graphs from graphs, which is quite cool. So we can use this to represent rules. Some people have looked at doing things recursively to generate some sort of recursive patterns and so forth. So this returns an RDF graph based on the matching construct clause, which is quite neat. Okay, our last feature, or last kind of query type, which is not very used, it's used in certain circumstances for linked data, which we'll talk about a little bit later in the course, is describe. So it's a non-normative feature. So Sparkle standard said, okay, we're going to add this describe thing, but we're not going to define what it returns. Yeah. So there's only really an intuition, a syntax and an intuition. So the intuition is if you use describe, what it says is give me some RDF data about the results. Yeah. So in this case, we have the same query as before, and we put describe star. So it says basically, give me some RDF data that describes all of the stars. And we would expect that it would be somehow a subgraph of this graph here. So in this case, we could say, for example, we could return, the most common definition is we return all of the triples where the result is a subject to say, okay, we have John Hurd is a person, yeah? Or Ian Zering is a person. Sometimes it will return all triples that mention that term. Sometimes it will return this, the triples where it appears as subject or object. There's a mix of different interpretations. It's not formally defined, yeah? But it's like intuitively describe this result to me. What is this thing? So return, it's an RDF graph describing the returned results. It's a non-normative feature. What should be returned is left open. Yes. So it provides some sort of syntax for engines that want this feature. These are the 4 query types. So in brief, we have select that returns tables, we have ask that returns booleans, and we have construct that returns RDF graphs, and describe that returns RDF graphs. Okay. So these are the 4 query types. By far the most commonly used is select. Construct and ask are relatively frequent, but maybe not so frequent as select. And then describe is really specific and is usually used internally for query engines. Principally because nobody knows what it's supposed to return. Yeah. Any questions or doubts? Okay, much like in SQL, we also have some solution modifiers. They are not so interesting because we've seen them before in SQL and in other query languages, but we have order by, possibly descending order. We have limit and offset, yeah? So you probably would have seen this before. Although in SQL, there are different ways to express this. It's a commonly supported syntax. So how might we ask for the second and third most recently released movies? So we'd use a basic graph pattern to get the first air date. Yeah. Then we'd order by descending date. Yeah. Because we want the recently released movie. So we want the dates to start from the most recent to the least recent. So we order by descending date. Then we use offset with 1 to jump. And then we apply limits to return the second and third most recently released dates. Yeah. So this would be essentially our query here. We get the dates of the movies. We order by descending date to get from the most recent dates to the least recent dates. We apply limits 2 to take 2, and we apply offset 1. So this is written in a confusing order, but it doesn't actually matter. So we're going to skip 1 result, and then we're going to return 2 results. Yeah. So if we don't apply order by here, then this query becomes non-deterministic again. So basically, if we have no order, then the order is non-deterministic, and what results we're given will be chosen non-deterministic. So the order of execution is always order, then offset, then limit. It doesn't matter if we change the order of in which order they're written. We can only change the order of offset and limit, which is a little bit messy. But if we write limit 2, offset 1, or offset 1, limit 2, it doesn't matter. We're going to apply offset first and then limit. Okay. So order by must always come before this, but this is already in the syntax. So we can't even, it would say this query is invalid if we try to put order by after the other elements. Okay, any questions or doubts? Okay, so we're into the last set of features then for Sparkle 1.0, which are kind of maybe a little bit more technical, which are name graphs. So I'm going to explain name graphs. And with that, we'll be done with Sparkle 1.0. So named graphs. What are named graphs? Named graphs are graphs that we name. Yeah. So something we haven't mentioned before, but in RDF and in Sparkle, there's this notion of a data set, an RDF data set or a Sparkle data set. And what's the idea? The idea is that we don't necessarily want to just manage one graph. Yeah, sometimes we want to manage multiple graphs. Yeah. So maybe we have different RDF graphs that come from different web pages, for example. So we can name that graph according to what web page it came from or what location it came from. So we have this idea of a data set, and a data set is composed of a pair of a default graph G and a set of named graphs. Yeah, every named graph is a pair with a graph and a name. Yeah. So we have a default graph, and then we have a set of named graphs. Yeah. This data set allows us to record and to separate different graphs, to be able to reference and manage different graphs in different locations. So a common use case, for example, as I mentioned, would be to store different graphs from different web pages. If we extract the RDF from a web page, to store that under the name of the web page. Yeah. So then later, if we wanted to, we could update just that RDF graph for that web page. Yeah? So data sets allow us to reference different graphs. So G, G1, GK, all of these Gs here are RDF graphs. And then N1 to NK, the names of the graphs are just IRIs. And they're supposedly here pairwise distinct. Yeah, we can't use the same name for two different graphs. Yeah. So that's what this means. G is called the default graph. This is basically the graph we refer to if we don't say any name. Yeah. And then each GI to NI, a pair of GI, NI is a name graph. Yeah, so we have a pair of a graph and a name. Yeah, so we can then reference, for example, give me the graph associated with N2, which is an IRI. Yeah, so we have our data set, which has a default graph and a set of name graphs. If every name graph is an IRI, that names an RDF graph. Yeah, that we can reference. So the core idea, again, is that Sparkle and RDF, we can manage, we can reference, we can talk about multiple RDF graphs. We don't always have to fuse them all into one RDF graph. Yeah. So this is very useful, for example, if we're managing different RDF graphs from different sources or different locations, and we can name them separately and reference them and update them and query them separately. Default graph is chosen if you don't specify a graph. Otherwise, you can explicitly select a name graph and you can, using its IRI name. So you can use its name and you can say, I just want to query this graph, or I just want to update this graph, or I just want to do something with this graph or this combination of graphs. So an example data set, here we have maybe an example where we have a default graph, and then we have some RDF files, sharknado.ttl and sharknado2.ttl. And we've loaded this into our Sparkle engine. And just to keep track of where the different data come from, we name these graphs according to what files they came from, what's their source. Okay? So we have sharknado.ttl graph here, and we have a sharknado.2.ttl graph here. Yeah, so these are IRIs. So in our default graph, we have information about Sharknado series, the first movie and the second movie. And then in sharknado.ttl, we have all the data we have about Sharknado, the first movie. And then in Sharknado 2, we have all of the information we have about Sharknado 2, the second movie. Yeah. So we're not managing one RDF graph, but we're managing several RDF graphs. So then Sparkle provides us some features where we can query different graphs or different combinations of these graphs. A query can pick an active data set from the named graphs. Yeah. So what does this mean? We have our data set, which is our fixed. Let me remove this for a second. We have our data set, which is what we index in our store, in our Sparkle engine. However, at query time, we can change this data set and say, I only want to query over this other data set that I'm going to build by selecting from the base name graphs that are there. So for this, we have two features. One is called from. So from is used to define a default graph for the query using graph names. If multiple graphs are specified, they are RDF merged. Okay? So we'll have to remember what RDF merged is in a second. And then we have from named that allows us to load specific name graphs as name graphs for the query. Yeah. So this is kind of a bit complicated, yeah, but we'll see examples. We'll get through it, hopefully. So the main thing for now is that we can use these features in queries to define a new data set. From allows us to define what the default graph will be of this query specific data set. From named allows us to define what named graphs we're going to include in this query specific data set. So we have from and from named. So using either feature clears the index data set. So if we use from or from named in a query, the first thing we do is we start from scratch. We just forget about everything that was in our data set, and we start building a new data set just for this query from scratch. Yeah. Okay. As promised, we have to remember what is an RDF merge. So the idea of from is we can name multiple graphs, N1, N2, N5, for example, and say, I want these graphs in my default graph. So what happens is from will apply an RDF merge of the graphs named by N1, N2, and N5, G1, G2, G5, and form a new default graph for the query. So what is an RDF merge? We talked about this in the first class, or second class, sorry, when we spoke about RDF. We said that when we merge these two RDF graphs here, we want to be careful not to have a false equivalence or a conflict on the blank nodes. We can't consider this blank node here and this blank node here to refer to the same thing if they're in two separate locations. Yeah. So when we do the merge, we should avoid a clash, what's called a blank node clash, where we merge the data for these blank nodes here, because now we have this information that we never had, that was never intended. For example, that lemon cheesecake has an ingredient that contains gluten. Oh no, that does have, I know that exists in this as well, sorry. That lemon cheesecake contains an ingredient that has pecan. Here we see lemon cheesecake contains an ingredient, has an ingredient that contains pecan, and that wasn't never originally stated. Yeah. So we're confusing things by merging the blank nodes. They're supposed to be kept distinct. So this is not the way to do it. We don't just apply a set union of the triples of the RDF graphs. We rather apply an RDF merge, which means that before we apply the union, we make sure the blank nodes names are kept distinct. Yeah. So in this case, we just add G1 here to this and G1 here. So we have B1, G1, B2, G1, B1, G2, B2, G2. And when we do the merge, we avoid this false merge of information on blank nodes. Okay. So that's the RDF merge. So we have this way of combining graphs for from. So let's have a look. Let's have an example, first a formal one, and then we'll look at what it looks like in practice. So we have here our data set is D, and we have our default graph G, and then we have G1, N1, G2, N2, GK, NK are named graphs. Our query data set, if we don't specify any from or from named, will be D. We just take D as our data set and we run our query on that. Yeah. If we specify in this case a query data set if we use these features here to build a data set, we have from N1, from N2, from named N3, from named N4. Yeah. So how do we form our data set from D based on this? What we need to do is we need to build our default graph from N1 and N2, and then we need to copy the name graphs N3 and N4 to be named graphs of the new data set. Yeah. So how does this work? We take the graphs associated with N1 and N2, which are G1 and G2. We apply an RDF merge. This gives us our new default graph. And then we take as name graphs G3 and G4, N3 and 4. Yeah, so we just select only these name graphs here. So this gives us a new query data set, and then we can query this data set, this query specific data set using some features we're going to discuss now. Here's another example. In this case, we have from and from. Yeah, so we have N1 and N2. In this case, our queries data set, D prime, will be just the RDF merge of G1 and G2, and we'll have no named graphs associated with it. Okay? So we can use from and from named to define a query specific data set. Yeah. So, okay, we have our data set defined for their query. We can use either the base one or we can define a new query data set. How do we actually query different parts of the data set? So within our where clause, we can then use this graph feature. Yeah. So this graph feature allows us to specify a name, the IRI of a named graph over which the pattern is evaluated. It can also be a variable that ranges over all named graphs. It does not access the default graph, and if not specified, the default graph is accessed. Okay? So if we don't specify graph anywhere, we only query the default graph. If we specify graph, if it's a name, we're only querying that name graph. If it's a variable, we're querying over all of the name graphs. Okay, so that's a lot. That's a lot of information. So let's start to look at some examples. Yeah, so that was a big dump of definitions and everything. So let's see some examples. So we have our example data set. Again, we have our default graph. We have sharknado.ttl and sharknado2.ttl. We have our query here, which says select distinct S where SPO uses no features whatsoever that we just discussed. Uses no from name, no graph. So what solutions would this query return? So any ideas? So we're asking for the unique subjects effectively. We have here all three variables which will match with any triple, and we say let's look for distinct subjects. Any ideas what the solution would what solutions this query would return? So the question is, what graphs are we going to query over? Are we going to query over the named graphs? No, we're not going to query over the named graphs. We said that if we don't specify anything, we always query the default graph and only the default graph. Yeah. So what we'll get in this case is the distinct subjects of the default graph, which will be Sharknado series. Yeah. We ignore the named graphs. Yeah. So we just get Sharknado series. Yeah. Okay. So yep.
How we can find the name of the graph unless we with the name of the file?
It's up to you. It's basically up to the person who maintains the data set. You can define the IRI as you want. A very common pattern would be to name the source that graph came from. So it would be like the web location, the document from which you extracted it, or it could be some other IRI that identifies this is from Wikidata, this is from DBpedia, this is from wherever. But a very common idea would be to have this name such that if you look up that name, you get the RDF graph that is spoken about. So that would be one pattern. Yeah. So in this case, we only query the default graph. Okay. So no graph clause is given, so answers come from the default graph only. In this case, we're using the from features, and the from features are going to create a new data set. Okay. So here we have select distinct S where SPO. So we're only going to get the distinct subjects from the default graph. But if we use from, our default graph changes. Yeah. So what would the answers be now? Any ideas? Not easy. So what will our default graph be in this query? Yeah, it'll be the RDF merge. There's no blank notes here. So it's essentially we take the union of these two graphs here. Yeah. And then the unique subjects in that would be Sharknado and Sharknado2. Yeah. So we use from to create a new default graph. And then our query is over the default graph. So we get Sharknado and Sharknado2 solutions. Yeah. So no graph clause. So answers come from the default graph. This is now defined by what we said in from. Yeah, we define a new default graph that overrides the data set, the base data set. Okay, we have from named sharknado.ttl, and then we have our query that does not use graph anywhere. We're looking for the distinct subjects. Any ideas what we'd return? Yeah, not easy. So one idea is that we'd return Sharknado. Yeah. Because here we're asking to query over the named graph Sharknado. The problem is that when we use from named, we're going to load this graph as a named graph. Yeah. And if we load it as a named graph, then this won't touch named graphs. This is not querying over named graphs, it's querying over default graph. Yeah. So in our data set, when we do this, we'll have sharknado.ttl as a named graph loaded, but our query here is only accessing the default graph, so we don't get any solutions. Yeah. So when we use from or from named, we basically remove everything that's gone. So our default graph has disappeared now. We say from named sharknado.ttl, so our default graph is still empty. We have a named graph, which is sharknado.ttl with a name. And then when we run this query here, there's no default graph, it's empty. So we get some empty results. Does that make sense? Yeah. Okay. No graph clause, so answers come from the default graph, but we just removed the default graph and we didn't add any new default graph with from, so no solutions. Okay, so now we're going to see graph. So graph allows us to access named graphs. Yeah, so we saw previously just querying all of the time the default graph. When we specify this graph keyword, now we're looking into the named graphs of the data set. Yeah. So if we don't use from or from named, we're using the base data set that's indexed in the query engine, let's say. So here we're looking for the distinct S and G, the distinct subjects and graphs, where graph G, SPO. Yeah. So what results do we think we would get in this case? How many results? So when we apply this graph here, we forget about the default graph, we ignore it. Yeah. Then we look for the distinct pairs of subjects and graphs. So one is Sharknado and Sharknado TTL, and the other will be Sharknado 2 and Sharknado 2 TTL. So we get two results. Yeah. So we get these two results here. We have distinct as well. So if we didn't have distinct, we would get how many results? We would get 1, 2, 3, 4. We'd get 4 results here, and we'd get 2 results here. We'd get 6 in total. Yeah. Okay, so the point here is that when we use graph, we're only going to query over the name graphs here. So we can use graph with a variable. So graph clause only ranges over the name graphs, and this is okay. Graph clause only ranges over the name graphs. This is because the default graph doesn't have a name. So what would we put for G here? We don't really have a value for G. We don't have a name for that graph, so there's nothing to return. Okay, we can specify a graph. Graph doesn't have to be a variable. We can say graph sharknado.ttl SPO, and we can get the distinct subjects. So how many solutions do we expect in this case? So in this case, we name a specific name graph and we say, hey, I just want to run this query pattern on this graph. And this query pattern is extracting effectively the distinct subjects. Yeah. So we'll get one answer, which will be Sharknado. Yeah. So we just get this answer here. Okay. What about in this case? So we have a from. We're going to change the data set now. We have from Sharknado.ttl. And then we have this query graph G SPO. And we want to get the distinct S's and G's. Any ideas how many solutions this will return? So when we apply from or from named, we remove the data set. With from, we create a new default graph, which is Sharknado.ttl. And what will our name graphs be? No, our name graphs will be empty. Yeah. So Sharknado.ttl will be in the default graph. Yeah. So we have no name graphs. Yeah. So in this case, we have no name graphs. This query is named graphs, so we don't get any solutions. Yeah. So no name graph specified. If we write from named Sharknado.ttl and then we apply graph, so we're going to load this not as the default graph, but we're going to load it as a named graph. Yeah. Then we're going to query this graph G here. And we're looking for the distinct subjects and their named graphs, the names of their graphs, sorry. So we have a named graph loaded Sharknado.ttl, and then we run this query here. And what will we get as a result? Yeah, exactly. This time it's loaded as a named graph. So we're going to get Sharknado and Sharknado.ttl. Yeah. So the graph axis is the one and only named graph. Yeah, it ignores this pattern again. We'll just ignore the default graph. It will just look at named graphs and return the results from there. The last example, I think, if I remember correctly, a more complex example. We have graph. Oh, what is this? Okay, I'm going to have to figure this out myself. From Sharknado2.ttl, from named Sharknado.ttl. So we're going to take Sharknado 2 into the default graph of the query. Yeah. We're going to take Sharknado in as a name graph for the query. Yeah. This first pattern here is going to query over the name graph, and it's going to get the graph and the triples for that. Okay. So that will return Sharknado.ttl and a result for every triple here. And then this part here has no graph, so it will go over the default graph. Yeah. And the default graph in this case is Sharknado 2. So it will basically give us XQO. So it will give us Sharknado 2 title, Sharknado 2, Sharknado 2 stars in zeroing. Then there's going to be a join between these two things. Yeah. So we're going to join this part here and this part here on the object. because we have the object variable in common here. Yeah. So what do we have in common in terms of objects here? We have Ian zeroing. Yeah. And then what do we return? XQ. Okay, Sharknado 2 and stars. Yeah. Hopefully. Yeah, okay, Sharknado 2 and stars. So that's not easy, even it's a bit challenging for me to go through this and see. So what's the point here? The point here is that this part accesses the name graph, which comes from Sharknado. This part here accesses the default graph, which comes from Sharknado 2, from the from. And we can have queries that mix or somehow do joins across different documents across the default graph, and so forth. So we can combine information from different places. Any questions about that? Tricky? Tricky. So yeah, the key point is we can use GraphG to access the named graphs. We can use, if we don't have graph, it accesses the default graph. We use from to load a new default graph. We use from named to load named graphs. Okay. Sparkle. So that's Sparkle 1.0. The next time we're going to talk about Sparkle 1.1. So we're going to talk about some new features, some things that would be familiar from SQL, some other features that are not related at all to relational databases, like querying plots. So yeah, today we've covered Sparkle 1.0. Then we'll have Sparkle 1.1. Any questions, Johns? All good? Okay, so in the lab on Wednesday, yeah, you're going to be given some RDF data, you're going to do some queries. We're going to practice with Sparkle queries a little bit. In RDF Playground. I think then afterwards, if I remember correctly, we'll be just querying directly Wikidata. So what's coming up this week? Labs on Wednesday. I think the reading groups are due on Thursday. Next week is feriado. I think the Monday is bank holiday. Is it? Yeah. So next week, if I recall correctly, what we're going to do is on Wednesday, we're going to define projects. So the idea would be we finish with the reading groups and then we start to think a little bit about projects. So there will be a class project. The idea would be we'll publish more information on the forum, but the idea would be to form groups for now, groups of 3. At most 3. You can use the same group as the reading group. There's no problem. There's no restrictions on what group you form. The idea would be to do something to take on some challenge or some problem or some sort of project using technology related from the course. So that could be OWL, it could be Sparkle, it could be whatever you've seen. The problem with these course projects is you haven't seen everything yet, but we can't start. We have to start now. So what you've seen thus far is probably the core. That's RDF. RDFS, OWL, Sparkle. This is kind of the core of the semantic web. So there's some other cool stuff we'll see that might come a bit too late to be applied for the projects. A very common type of project would be to take 2 data sets that are complementary or interesting, convert them into RDF to integrate them, and then demonstrate some sort of Sparkle queries over that, where you do some queries over the combination of the 2 sources, for example. Another common type of project would be to define an ontology for some sort of domain, and then to use a reasoner to be able to reason about certain aspects of the domain, or look for inconsistencies, or to look for the performance of reasoning. So there's a variety of different types of options. Another type of project is to build some sort of application over an existing data set. For example, build an application on top of Wikidata that does something fun, that uses Wikidata as a backend. And then you build an application that sends Sparkle queries to feed or to get data from Wikidata and build some web application or something. Yeah. So we're pretty flexible in terms of what the project would be, but it has to use obviously some elements of what a core element of the project has to be what you've learned in the course. Yeah. So the idea would be to finish with the reading groups, and then but we can also start to define the groups for the projects. We'll have a project session on Wednesday next week, where we'll be there and we can answer questions about the projects. You can start to look with your groups about what kinds of topics to do. We'll be there to answer questions. Or if you come with some ideas, we'd be happy to discuss them on Wednesday. next Wednesday. So the Sparkle 1-1 class will continue in 2 weeks. Yeah, I guess as well, I think the last lab is probably one of the more conceptually challenging labs. Do people have questions about the last lab? I can stay around for a while in case there's questions. Any questions overall about Sparkle 1.0 course? No? Okay, in that case, I will see you on Wednesday for the lab. What happened to the animation here? Oh, animation's not working very well. Okay, here we go. Okay. See you in Zoom as well.